Apex 2012 includes a wide range of enhancements in the area of ray tracing. You see here a simple light pipe that we're going to use to demonstrate some of these new features and functions. In this particular case, I have a short, 25 millimeter long light pipe that starts at the input end with a aperture size of 5 millimeters, and at the output face, the aperture width is 10 millimeters. And what we have also coming into this light pipe is a simulation of, for example, the output of an LED, so a Lambertian source that is slightly smaller than the input face, sending light downstream. Now let's take a look at some of these enhancements to Apex that are going to help with the analysis of systems such as this. First thing we're going to take a look at is I'm going to go to the Project Settings tab. Some new features on the Project Settings tab are very important for analyzing not only light pipes, but almost all illumination systems. In this particular case, of course, what we're going to want to do is, because this light pipe functions on the basis of total internal reflection, I am going to turn on the averaged S&P polarization calculations. But the most important new feature is right down here. For those of you who've seen Apex in the past, we've added a couple of additional ray trace options, one of which is for ray path analysis. If I select this option, and as you can see, I've already turned on this feature, what will happen is during the ray trace, information about how all of the light propagated through the system will be saved, and I'll be able to analyze that information later on the basis of individual paths. So not only will I know how much energy made it through my system, I'll understand a lot more about how it made it through the system. And what I'm going to do is I'm going to start by doing a simple ray trace. Now, we're not going to display all of the rays, just a subset of them, but let me go to the Trace tab right here, and this is where I have my different ray trace options. I can also get back to my project settings now directly from my ray trace tabs, because sometimes we forget to set the settings appropriately before we hit the trace button. But you'll also notice that as part of the trace, there is a step trace option that has been added. What this allows you to do is to trace the rays from object intersection to object intersection. So let's take a look at this, and I'm going to reorient the pipe so we get a little face-on view of it, and select this step trace option. What this allows me to do is we're going to start a new trace from the source, and end steps is how many objects do we want each ray to intercept. And we can either travel through a surface at the end, so in other words, see the properties of the ray after they reflect or refract at a surface, or we can stop the ray an infinitesimal distance in front of the surface. So in other words, understand or analyze the rays before the refraction or the reflection takes place. And in this particular case, we'll just look at a single step. So we'll trace our rays until they intersect their first object. And since we have a Lambertian distribution of rays, we should see rays hitting at different locations along the pipe, and potentially even some rays going all the way through the pipe. So let's just click on the step option right here. Right now, we're creating the geometry. This is also another enhancement that's available in Apex 2012. Ray trace speed is also enhanced with the addition of geometry recognition capability to the ray tracing algorithm. And you'll notice as we click on the step button, because we have continuous stepping, we've now traced the rays to their next interface. So the first time the rays reach the front face and just refracted in, or may have been lost backwards to a Fresnel reflection, and now they've reached their first intersection with the light pipe itself. Most of the rays will hit along the side where they would totally internally reflect back into the pipe, although those rays exiting the source at a very narrow angle will actually travel right through the pipe without it hitting the sides, and then just become incident on the output face. So in those instances where you'd like to see what happens to the light as it propagates through a subset of the geometry in the system, the step trace option is the perfect tool for that type of analysis. But now what I'd like to do is trace all of the rays through the pipe and see what happens there. So let's close out of our step trace and do a complete ray trace through the system. So as you can see, our ray trace has completed. And let me rotate the view around a little bit, give us a better view of what's happening. Now we can see some rays appear to be going off into space. That's simply due to the Monte Carlo simulation. Some of the energy that reaches the front face of the pipe will be lost due to Fresnel reflection, and that's simply what those rays are representing. But the rest of the light is propagating through our light pipe, hitting the pipe along the edges, TIRing until it exits out and reaches in this case, my detector space right here. So let's take a look at the detector. What I'm going to do is highlight the detector, and I can go to my analysis tab. And what we might want to look at is both an irradiance and an intensity distribution at the output face. So the first thing I'm going to do is just to click on the irradiance tab. And I'd like to increase my resolution a little bit. I've traced a large number of rays. So now what I'm going to do is simply look at the irradiance plot by clicking on the OK. And here's the data. Now, at first glance, we can see that this looks relatively uniform. We can certainly see that the irradiance is a bit lower towards the center, and that's simply because with the cross-sectional changes in this light pipe, we really haven't traveled long enough to really get a nice uniform distribution of the energy after we propagate through the light pipe. It's important when doing light pipe analysis that you make sure you travel, that your light pipe section is long enough to fully homogenize the beam so your light pipe represents the real physics of your simulation. But similarly, you don't necessarily have to make the light pipe the full length, because the longer light pipe simply will take longer to ray trace, and once you've reached a certain length, the output isn't going to change. So what I'd like to do is simply increase the length of the light pipe and show you how that affects the results of the simulation. And to do that, we'll simply select our light pipe here. And if I zoom in, I need to find my length dimension right here. And instead of this short length, let's increase it, say, to 150 millimeters. And let's rebuild the geometry. And again, let's go to an orientation where we can see what will happen. And of course, obviously, since I've still got the same output size, these rays appear to be missing, but that's simply because we're able to look at old ray traces as well. So let's close this, and let's just ask for one more ray trace. All of our project settings have been stored, so we don't have to make any modifications to the settings area. We will also be saving the path data for this file as well, and we'll take a look at the path data once we look at the results of the final ray trace. Okay, so we've now completed this ray trace, and again, we'll first take a quick look at the analysis. So, simple analysis might be, where is all the energy after the ray trace? So if I click on Summary Statistics, you'll notice another one of the features in Apex 2012 is this split view. What this allows you to do is to look at the results of the simulation as well as in this particular case, the summary statistics. Now you say, how is that useful? Well, if you look in front, we see where all of the energy is. And the disk represents my source, the physical geometry of my source. The plate is my detector surface. And you'll notice most of my energy, 87% of my energy, did indeed reach my target location. And then the faces of the rectangular pipe are my light pipe. But how do I know which one of these faces represents which part of the geometry? Well, for example, let's take a look at this information right here. And I say, okay, what is this 2% of the energy? There are 12,000 rays there. What's happening? Well, I'm just going to select this information and say highlight surface. And I look, and you can see highlighted in blue here is the input face of my light pipe. In other words, these are Fresnel reflections that left my light pipe at angles such that they did not get captured on an absorbing surface of my dye representation. And similarly, these rays right here, if I highlight this surface, are rays that were last incident on the output face of the light pipe. But as mentioned, the rays of interest to us are these rays right here, which are those incident on my detector location. So now what I'm going to do is enlarge the view of the simulation one more time. And as we look through it, we can see all of our rays, and again, all sorts of ray paths. What we'd like to do is get a better idea of how did the light travel through this light pipe. Now, we saw a little bit of that when we did the single steps previously through the shorter pipe, but let's take a look at this light pipe. I'm going to start by looking at an irradiance profile one more time to make sure we've got a fully homogenized beam. So let me just click on the irradiance option. Apex remembers that I liked a little bit higher resolution, so I'm just going to click on OK. And indeed, we can see that we have a much better uniformity out of this longer pipe. So there's no real need for me to do a simulation through a pipe that's even longer, because I'm really not going to change the output significantly. And of course, I always have the option of coming in here and doing a little bit of statistical averaging, and maybe in this particular case, I'll average by fold because of my symmetry. Click on OK. I've created a new average data set, and let's take a look at it. So again, a nice uniform distribution, as would be expected from this light pipe. Now, the other question I might ask myself is, I have a Lambertian light distribution coming into the system. What's the angular distribution of the light coming out of the pipe? And again, to simplify things, I'll pre-select my target surface. Only this time I'll look at an intensity calculation. And I can look at intensity, and in this particular case, let's just look at it in direction cosine space. And I'll just click on OK. And here's my results in a false color form. And I'll notice if I come on over here and look at the edge, I notice that in direction cosine space, my cutoff is at a direction cosine of 0.5. And if I do a quick back of the envelope calculation of étendue or angle area product, exactly what I would expect, that all of my light should fall at a direction cosine of approximately 0.5 or less. So basic radiometry seems to hold. But here's where the new functionality of Apex truly comes into play. I'm going to select this option here, which is the path data. You'll notice that my target surface is pre-selected, so what this is going to do is go through all of the path information and allow me to interrogate information about all of the energy that is currently on my target surface. So let me just click on that, and we'll start by looking at all of the possible paths, and click on OK. And in a few moments, we will have a new table of data. Now here's the result of our paths analysis, and it also gives us this split view screen. And let's take a look first at some of the information in our paths table. The first information, the first column, tells us that there were 39 separate paths through which light reached our target surface, and a total of 437,000 rays, and about 87% of our initial energy. By default, the table is sorted in terms of total flux, or the percentage of the flux in each path, and the next column over is the number of surfaces hit. This is a fully searchable database, so if I choose any of these columns, for example, path number, I can resort the data based on whatever column I've selected. But for our purposes, the percent of the total flux is actually a very useful category. And you'll notice next to it are the surfaces hit. We know at a minimum the light had to hit the input face and the output face in order to reach the target. Because of the number of surfaces here, what it looks like is most of those rays also had to hit